This is lecture number 23 of the course AU 203 Statistics and Quality Control. The lecture topic is sampling and sampling distribution. So we will start our discussion differentiating between two important terminologies, parameter and statistics. And then the idea of sampling, the concept behind sampling, and the sampling distribution, and calculating the mean and variance of a sampling distribution theoretically, and in the end we will look into some problems as well. So what is parameter? A numerical characteristic of a population or a model which is actually under study. So it could be any numerical characteristic. It could be mean, it could be variance, it could be standard deviation. So if if that characteristic is related with the population which is under study, it is called as parameter. And statistics is the numerical characteristic of a sample, and sample is taken from a population. So sample is always a subset of a population. So let's say we have some population and represented by circles, and let's say some of those elements of that population has been picked and make it a sample. So all these black spot as taken as a sample. So we need to predict the population using that sample. So observations taken in this sample is evaluated, and the parameter and the numerical characteristics of those samples are actually called as statistics. So x bar is the mean of the sample, s square is the variance of the sample, s is the standard deviation of the sample. So these are the numerical characteristics related to the sample, and the purpose of getting information from this sample is to predict this population, characteristics of the population. So characteristics of the populations could be mu, which is actually a population mean. Sigma square is variance of the population, and sigma is the standard deviation of the population. In most of the cases, we use the Greek letters to represent parameters, which is representing the characteristic of a population. And English alphabets are usually used to represent the characteristic of a sample, or in short, we call it statistic. So most of the time, we are not able to find out the characteristics of the whole population. So the population parameters are most of the time are unknown because they are large in number, and we usually for a large population, your population size is large, then the parameters doesn't change. So in most cases they are constant or fixed. Whereas in statistics, which is taken from a sample, they are not fixed. It varies from sample to sample. Even though we have a same population, and we can have different samples from the same population, and each sample would have a different characteristics, so we call it different statistics. So the terminology parameter is just a characteristic of a population, whereas statistics is a characteristic of a sample. Okay, what is meant by sampling? Sampling is a simple process of selecting some part of the population to estimate something of interest of about the whole population. So the whole population cannot be analyzed, and we always need to take sample out of that population, and we need to predict the behavior of the population through that sample. And there are different types of sampling techniques. For example, let's say you have a population, and the population parameters are the population size represented by capital N, mu is a population mean, and sigma is a population standard deviation. So what we do is we take small part of that population called as samples, and here let's say we have evaluated the mean of the first sample, which is represented by x bar. So x1 bar would be the mean of that sample, x2 bar is another sample, and x3 is another sample. So x3 bar is the sample of the another sample of the mean. So if we look at the distribution of those sample means, then the first sample mean is x1 bar is plotted here, x2 is plotted, x2 bar is plotted here, x3 bar is plotted here, and here n is actually the size of the sample for each of the samples. So x1, let's say you can think of population is comprised of 1,000 objects of a batch, and out of that each sample of 10 size is being selected. So 10 objects taken from that 1,000 objects, and calculate the average. Similarly, another sample 10 objects taken from the same population, so that would contribute to another sample. And if we plot the mean of those samples, there is a distribution of the sample means. So this would be, if this population is normal population, then the sample means would also be normally distributed, and we will look into detail later. There are two broad classification of sampling. The one is called a random sampling or probability sampling. In random sampling, each object of a population, or each member of a population, has an equal chance of being selected. So that is why it is called as random sampling. And in random sampling, it could be, there are different types. It could be a simple random sampling. It means just the whole population is interested in analyzing the population through sample, and sample is taken from the whole population randomly, choosing members from that population. That would be called a simple random sampling. Or if we have stratified depending upon the groups, for example, young groups or mid-age groups and old groups, and then it would be each strata, or then this would be called as, so what we do is we make a sample from each strata. So it is random in each strata. For example, the sample taken from the children, so all children, make it a one strata or a group, and we randomly pick members from that strata. Then it would be called as stratified random sampling. Or sometimes we make it a systematic pattern that say, let's say we will pick elements in first hour of an operation. So every first hour of an operation, start of the day, you are going to pick random samples. So that would be called as systematic sampling. Or sometimes some clusters are formed, and we just take samples from those clusters, but each cluster would have an equal opportunity of being selected. So there is always an objectivity involved in random sampling, because each member, whether a strata or a cluster or a system, have an equal opportunity of being selected. In contrast, another non-random sampling or non-probability sampling, there are different types of those non-random sampling. Convenience sampling, in which it depends upon, in non-random sampling, not every member have not an equal chance of being selected. So there is a subjectivity or biasness associated. So if the researcher has a convenience of taking a sample, so based on the convenience of the researcher, that sampling is actually called as convenience sampling. And sometimes the researcher has a prior judgment of the particular sample to be taken, and in that case that sampling would be called as judgmental sampling. And sometimes some quota is associated, for example, if you are interested in cricketers, so let's say you are going to pick bowlers, or you're going to pick wicket keepers, or you are going to pick batsmen. So that would be a particular strata in which you make it a quota, and once there is no randomness, then it would be called as a quota sampling. And sometimes what we do is we select few people as a sample, and then we ask these people to select more people for research, for study of the population. Then this type of sampling is called as snowball sampling. So keeping in view the effect of a snowball, where once you roll a ball from the hill top of the mountain, then the size of the ball is small, and gradually it takes a more part of the snow and make it a bigger size ball. So in this way, initially your sample size is smaller, but once it grows, then the sample size increases, because these initially pick up samples have a choice of picking their own samples, so that the whole sample size has grown up. This is actually called as snowball sampling. Uh, okay, so what we are interested in most of these cases, we will be interested in simple random sampling. So this is in the course, we will only be dealing with the simple random sampling. Uh, the probability distribution of a statistics is actually called as sampling distribution. So statistics means it is always taken from a sample. So what is the probability distribution of the characteristic of a sample is actually called as sampling distribution. So just like in probability distribution, what you take is you have a sample space, and there is a certain probability associated with each outcome of an experiment. In this way, you will be able to draw a probability distribution. So if your parameter, if your characteristic of an interest is taken from a sample, that we call it an statistics, and there is a distribution of the probability associated with the statistics, is called as sampling distribution. So we have already seen the example of the sample mean. Sample mean is statistics. So how each sample mean is distributed corresponding to different probabilities. So if it is on the higher on the peak, it means it is a more probable. If it is on the tail side, it means it is less probable. Then the distribution would be called as sampling distribution. So as we have seen that the distribution is arises because of the fact that even though the sample size for each sample is same, but you have taken samples from the population, and each sample would have a different sample statistic, whether it is a mean, whether it is a variance, whether it is a standard deviation. So these sampling parameter sampling characteristics called statistics vary from sample to sample. Let's say if we have a sampling distribution of the mean. So initially we have certain population represented by a random variable x. So different values of x are possible. And what we do is we take a sample from that population to calculate the mean of the sample. And the x bar represent the mean of the sample. So x represents the random variable or population elements. So if for each sample you take different means and all these means are plotted, there is certain distribution of those sampling means or sample means. So this would be called as sampling distribution. Uh, so here this sample mean is not a single value, but it can take any value. So we would call that sample mean to be itself would be a random variable. So each population parameter, population characteristic that we call it a parameter is also a random variable, and statistic which is taken from a sample is also a random variable because it can take any value. Okay, just take a simple example. We have a population comprising of three elements. So there are 2, 4, 6, these even numbers comprising of your population. So it is a very small size population having only three parameters. So we need to make it a sample of size 2. So in out of these three elements, we need to take a sample of 2 elements. So how many and what we are doing is with the replacement. So once we pick an element, Let's say either we pick 2, once we are picking another sample, then we are replacing the 2 back into the pot. So it means this is called as with replacement. So the question is how many total possible samples you are going to form with that population. If you have, so 2 and 4 could be one sample, and 2 and 6 could be one sample, 4 and 6 could be one sample. So if you look at and once you are with replacement, it means you can put 2 back again. So one of the possible sample could be first element is 2 is picked, and once you replace it, then the second element of your sample would also be picked 2. So in this way 2 is one sample. 2, if you pick first element is 2 and second you pick 4, so it could be another sample. Or if you pick first element 2, second element 6, so it could be another sample. Or if first element is 4, the second element is 2, it could be another sample. So here in this particular population with the 3 elements in that, you are going to get 9 possible samples, and you can work out it with this formula as well. If capital N represents the population size and small n represent the sample size, then the population size is 3 and 3 to the power 2 is 9, so you are going to get 9 possible samples. So let's say if you have 4 elements, then 4 to the power 2, if your sample size is 2, then it would be 16 possible samples out of that 4 elements. So and keep in mind, we are having a case in which we are, once we pick an object, we are replacing it back. So this is something with replacement. Okay, the next question arises, what will be the characteristic of that population, because our population comprising of only 3 elements. So we'll be interested in the population mean and the population variance. So we know how to calculate, because 2, 4, 6 are the elements of our population, and once we calculate the mean, you know that total elements is sum of the x is 12, and 12 divided by 3 would be 4. 4 becomes your mean value, mean of the population. Since it's a very small size population, you can easily estimate the mean of the population by taking the sum of all the observations and divide by the population size. Here population size is 3, so you are going to get 4 becomes your population mean. X is your observation. So if you take the difference between your observation with your mean value, then 2 minus 4 would be minus 2, and 4 minus 4 would be 0, and 6 minus 4 would be 2. So you're going to get the difference of your observation with the mean of the population, and since it could be a negative and positive numbers, if you take the square, you are going to get this. And you easily from this formula you can calculate the variance of this population, which is by definition the difference with the mean, and take the square and take the sum. So sum, you are going to get this numerator is 8 here, and 3 is your population size, and 8 upon 3 becomes your variance. Or if you take the square root of 8 upon 3, it would be your standard deviation. So from that particular example with the 3 elements in the population, we have calculated the population mean and the population variance. Let's say what will be the sample mean and the variance. So for that particular 3 element population, if you take the samples, you have 9 possible samples, and now we are interested in the sample mean and the sample variance. So x bar is representing the sample mean. So 2 and 2 are the elements, so sample mean would be 2 plus 2 divided by 2, or 2 plus 4 divided by 2, that would be the sample mean. So you have calculated the sample means of all the samples, all 9 samples, and this would be the sum of the mean values of the sample, and this would be the individual value of the sample mean if you subtract it with the population mean. Mu here is a population mean. So sample mean can be easily calculated just by calculating the sum of each element, each sample elements, and divided by the sample size. So here 2 elements in each samples, so n becomes 2. So you got the sample mean, which for each sample. And if you look at how to write it, we usually write it the sample means by calculating the all these means of the samples. If we are interested in calculating its mean value, so first take the sum of all the mean values, all the mean, you take the sum, and k represent the number of samples, actually not the sample size, because k comes out to be 9 here, because we have 9 samples of each. 2 is your sample size for each sample. So it is actually the mean value of the sample mean of a sample mean. So we usually another way of writing down mean of the sample mean, x bar represent, it is actually the mean, mu represent the mean, and x bar represent that it is the sample mean. So here the sample means comes out to be sum of the sample means. So these x bars are sample means, and you take the sum comes out to be 36, and divided by k comes out to be 9 here. Then 4 would be your sample mean. And similarly, we can work out the sample variance, which is the sample mean, how it varies with the mean value. Take this difference square, and so you are going to get this 12, this sum, and this 12 divided by k, that would be 9, that would be your sample variance. So sigma square is a variance, and x bar is this subscript x bar represent, it is actually the variance of a sample mean. So here if you look at earlier, the population mean was 4 and the population variance was 8 by 3. So if you look at the comparison, that your sample mean and population mean are identical values. So this is your sample mean, which is 4, and your population mean was 4, so both are identical. And if you look at the sample variance and the population variance, they are not identical. So the relationship is the population variance, if you divide by the sample size, you are going to get the sample variance. Here sample variance is 4 by 3, so is 4 by 3 divided by here it is 8 by 3 is your population variance. So population variance 8 by 3 divided by 2, it would be 4 by 3. So 4 by 3 becomes your sample variance. So the relationship between sample mean and sample variance is this. Sample means and population mean are identical. Sample variance is the population variance divided by n. And if you have to calculate the standard deviation of the sample, then that would be equal to under root of sigma square over n, where sigma square is representing the, or if you take the square root, it becomes sigma would be representing the population where standard deviation. Okay, we take that same population, but this time what we are doing is we are not replacing the first element which you have chosen. So that is called as without replacement. So in that case, how many total possible samples are there in a population? So obviously, once you won't replacing, once you pick 2, then you cannot pick 2 again, because you have not replaced back in the pot. So you can only pick either 4, or you can either pick 6. So there are 3 possible samples are there, and formula could be because a capital N combination is small n. Capital N is our population size, and small n is the sample size. So we have a 3 element population. 2, 4 and 6 are the elements, and we are picking 2 as your sample. Then the 3 possible samples are there. Okay, the next we are interested in what will be the sample mean and the sample variance. So exactly we have evaluated the sample mean, because here 2 and 4 is the first sample, 2, 6 is another sample, and if you take the sample mean, it would be 4 plus 2, 6 divided by 2, that would be 3. 6 plus 2, 8, 8 divided by 2 would be 4, 6 plus 4 would be 10, 10 divided by 2 would be 5. So this would be your sample means. And if you take the sum of all the sample means, you can calculate the mean of those samples. So sum of all the mean values divided by the total number of samples. Here the sample size k is 3. So you got the sample mean with this case, and if you calculate the variance of that is 3 samples, you are going to get the variance, which is the mean of the sample subtracting its mu x bar actually, and take the square. You are going to get this. So the relationship here is, if you learn in the case of without replacement, your sample mean would be the same as the population mean, and your variance in that case would be different from the with replacement case. In with replacement case, your variance would be sigma square over n. Here you have some correction factor, n minus small n and capital N minus 1. So here if you look at n is 3 and small n is 2, and if you substitute, you will be able to calculate this sample variance without replacement case. Okay, so what we have seen here is from this particular study, the distribution, sampling distribution of the mean values of the samples. So you have a population where the population parameters are mu and the standard deviation. You take SRS represents simple random sample. So if you take a simple random sample of size n, and for each sample the sample size is identical, so you are going to get the mean value, and all these mean values if you plot, and you can see the mean values would be the same as the population mean. But the variance is, or actually here it is not showing variance, but it is showing standard deviation, because if you take the square root of sigma square over n, then square root of sigma square would be sigma, and under root n would be representing the standard deviation of the mean of the sampling distribution. We call it a sampling distribution of the sample mean. So the standard deviation of this sampling mean would be calculated by the formula sigma over under root n. Okay, we can see the mean and the variance of the sampling distribution of the means. Suppose that we have a random sample of n observations. X1 to xn is taken from a population x with the mean value mu and variance sigma square. So the sample mean would be for each observation you take it a sample, all the elements of the sample, the characteristic has been sum up together and divided by the sample size to get the sample mean. We can write the same expression x1 over n and x2 over n like that too, if I am interested in calculating the mean value of the sample mean. So expected value of the sample mean would be the mean value of the sample mean. So it would be the expected value of this term plus this term and plus this term. As we know the property, it would be 1 upon n1. Out of that expected value of the first sample, second sample, third sample, n sample. So the expected value of the sample mean would be here n is common, take out common, and if you take the sum, as you know that once x1 x2 are normally distributed, then their sample mean would also be normally distributed. This is actually we have learned in the so-called reproductive property of a normal distribution. So we can say that when your x is your random variable, and if it is its population is normally distributed with mean mu and variance sigma square, then take the population. So each population, each sample from the same population would have the same mean values. So mean value of the first sample, mean value of the second sample, and the nth sample would be mu. So if you take the sum, it would be n times mu divided by n, then n and n cancels out. So the we have theoretically also seen that the mean of the sample mean is actually the population mean, which is mu. And we have already seen in these two examples with replacement and without replacement that the mean of the sample is actually the equal to population mean. And theoretically, we have already also have seen the same thing. Or the same thing, this actually expected value of the sample mean means actually it is the mean value of the mu represent the mean value and x bar represent that it is a sample mean. So mean of the sample mean is actually the same thing as the population mean. And this is what we have proved analytically, and in the previous examples for three size population with replacement and without replacement we have seen the same effect. Okay, now for the same case, we have a random sample of n observations, and which is the population is normally distributed with mean, mu, and sigma square variance. The sample variance would be the variance of the each sample means. So would be variance of x1 over n and variance of x2 over n, and we know the property 1 upon n, it becomes 1 upon n square, and take out common 1 upon n square. So it would be the variance of the first sample, second sample, or nth samples. According to this reproductive property of this normal distribution, we can say that the variance of this sample mean would be also the population, once x population is x1, x2, xn, and if you take different random numbers, each random numbers x1, x2, xn would be behaving exactly in the same manner as the population, because the samples are taken from the normal population, and random variable for the population is normally distributed with mean, mu, and sigma square. So according to the reproductive property, all these variances for each sample would also be normally distributed, and their variance would be sigma square. So if you take the sum, it would be n times sigma square, and n here, one n cancels out. So you got the same formula for variance of the random variable as a sample mean actually. So sample variance would be sigma square over n. Sigma square is actually the population variance and divided by the sample size. That would be the formula which we have already proved from the previous examples. Now we have seen it analytically, exactly the same result. So the mean and variance of the sampling distribution of the mean would be, the results would be represented like x bar is the sample mean, and the mean of the sample mean would be the same as population mean, and the mean and the variance of the sample mean would be not exactly the population mean, but population variance, but population variance divided by n. And we understand that this is the case where we are replacing it with the replacement. You have some correction factors of capital N minus small n over capital N minus 1. So this is we have derived, and we can see that using this fact that x is a random variable, which is any characteristic from a population. So it is actually called as represented by a population parameters. For example, mu and sigma square are their population parameters, and we know when your random variable is normally distributed, then if you take samples from this normal population, and these samples has, and there, if you look at their sample means, and their sample means would also be normally distributed, but here their distribution would be mean value is same as the population mean, and the variance would be sigma square over n. So this is an important fact, and mu represents the population mean, let's say, and let's say if you have a population which is has a distribution like this, so if you are interested in working out not the population x but the sample mean of that same population. So X bar represent the mean of that population, mean of that sample taken from this population. So it would be first mean would be first sample would be x1 or x2. Here, as you look at the variance of this sample mean, the formula is sigma square over n, which represents that as the sample size is increasing, the variance is decreasing. So if you look at your smaller sample size, let's say 4, then you have this distribution. Initially, you have a bigger spread, but the sample mean distribution of the sample mean would be having a variance of sigma square over n. Your sample size increases, then you see once sample size goes to 10, then your variance is also decreasing. Obviously, the standard deviation is also decreasing. So this is an important relationship between the observation and its sample mean. That as the sample size increases, the sample variance would be more going towards shorter tail, and so the data would be going towards the central value of the data. And so it would be more probable that your sample mean would be as we know that a sample mean is always the same as the population mean, and the sample variance is inversely proportional to the sample size. So more the sample size, smaller would be the sample variance. So this width is representing the standard deviation of the distribution of the sample means, and this distribution, this variance is decreasing as the sample size is increasing. And we can see it numerically by taking different samples. We will see it in the mini tab later. The same fact which we have proved it analytically, and with the two examples of taken a sample of sample size of 2 from a population of 3 3 elements of population. Okay, now let's see how we put this idea into numericals. Let's say an electronic company manufactures resistors, and their mean resistance is 100 ohms and the standard deviation is 10 ohms. So this would be the population mean, and this would be the population standard deviation. And it is mentioned that the distribution of the resistance is normally distributed. It means the population belongs to a normal distribution. We need to find the probability that a random sample of size 25 resistors will have a mean resistance of fewer than 95 ohms. So we are taking a random sample of size 25, and we are interested in calculating the probability that the average resistance or the mean resistance is less than 95 ohms. So first part of this population is, let's represented by x, a random variable, and we know that the random this population is normally distributed with mean value sigma, and variance is 10 square. Because derivation is 10, then the 10 square would be its variance. What we are doing is, from that population which is normally distributed, we are taking different samples, and the sample mean would be x bar, would be representing the sample mean, and we need to calculate the probability that the sample mean is less than 95 ohms. That is what is intended in the problem. So what I need is, I need to look into the distribution of the sample means. So first I calculate the mean value of the sample means, that would be the expected value, and we know that from our theory, in both cases, with replacement and without replacement, the sample mean is actually the population mean, and here population mean is 100 ohms. And we know the variance of the sample mean would be the population variance of the population divided by the sample size. Here standard deviation is 10. 10 square would be 100. 100 divided by 25 would be 4. So 4 would be the variance of the sample, and we can assume that the each sample mean would be according to reproductive property of normal distribution, would also be normally distributed. So x bar could take any value, and here x bar is 95, and if you take the mean of the sample mean, that would be 100, and the standard deviation of the sample mean would be under root 4. So if you calculate, you will be able to calculate the z value, and from the table, and you can calculate the corresponding probability for z, when x bar is 95, then z is minus 2.5, then only 0.62% is the probability that your sample mean would be less than 95 ohms. As we know that its population mean is 100, and the variance of the distribution is 4, so its square root would be 2, and for that particular distribution, this is a very small probability that your resistance could be smaller than 95 ohms. So if, let's say, what will be the probability that it is greater than 95 ohms would be, if the problem is, then it would be 1 minus 0.062. So because that represent that area. So this is how one can solve problem related with the sampling distribution of the mean values of the sampling distribution. Actually, sampling distribution means always the distribution of statistics, and statistics is always taken from a sample. Okay, this is where I stop this lecture.